LAN switching is a form of packet switching used in local area networks. Switching technologies are crucial to network design, as they allow traffic to be sent only where it is needed in most cases, using fast, hardware-based methods. Layer 2 switching. Layer 2 switching uses the media access control address from the host's network interface cards to decide where to forward frames. Layer 2 switching is hardware-based, which means switches use application-specific integrated circuit to build and maintain filter tables. One way to think of a Layer 2 switch is as a multi-port bridge. Layer 2 switching provides the following: hardware-based bridging, wire speed, high speed, low latency. Layer 2 switching is highly efficient because there is no modification to the data packet, only to the frame encapsulation of the packet, and only when the data packet is passing through dissimilar media. Layer 2 switching is used for workgroup connectivity and network segmentation. This allows a flatter network design with more network segments than traditional 10-base-T shared networks. Layer 2 switching has helped develop new components in the network infrastructure. Server farms or servers are no longer distributed to physical locations because virtual LANs can be created to create broadcast domains in a switched internetwork. This means that all servers can be placed in a central location, yet a certain server can still be part of a workgroup in a remote branch, for example. Intranets allows organization-wide client-server communications based on a web technology. These new technologies allow more data to flow off from local subnets and onto a routed network, where a router's performance can become the bottleneck. Limitations. Layer 2 switches have the same limitations as bridge networks. Bridges are good if a network is designed by the 80/20 rule. Users spend 80% of their time on their local segment. Bridge networks break up collision domains, but the network remains one large broadcast domain. Similarly, Layer 2 switches cannot break up broadcast domains, which can cause performance issues and limits the size of your network. Broadcast and multicasts, along with the slow convergence of spanning tree, can cause major problems as the network grows. Because of these problems, Layer 2 switches cannot completely replace routers in the internetwork. Layer 3 switching. The only difference between a Layer 3 switch and router is the way the administrator creates the physical implementation. Also, traditional routers use microprocessors to make forwarding decisions, and the switch performs only hardware-based packet switching. However, some traditional routers can have other hardware functions as well in some of the higher-end models. Layer 3 switches can be placed anywhere in the network because they handle high-performance LAN traffic and can cost-effectively replace routers. Layer 3 switching is all hardware-based packet forwarding, and all packet forwarding is handled by hardware ASICs. Layer 3 switches really are no different functionally than a traditional router and perform the same functions, which are listed here: determine paths based on logical addressing, run Layer 3 checksums, use time to live, process and respond to any option information, update simple network management protocol managers with management information base information, provide security. The benefits of Layer 3 switching include the following: hardware-based packet forwarding, high-performance packet switching, high-speed scalability, low latency, lower per-port cost, flow accounting, quality of service, switching. The switching algorithm is relatively simple and is the same for most of the routed protocols. A host would like to send a packet to a host on another network. Having acquired a router's address by some means, the source host sends the packet directly to that router's physical address. The protocol address is that of the destination host. The router examines the packet's destination protocol address and determines whether it knows how to forward the packet or not. If the router does not know how to forward the packet, it typically drops the packet. If it knows how to forward packet, it changes the destination physical address to that of the next hop router and transmits the packet. The next hop may be the destination or the next router, which executes the same switching process. As the packet moves through the internetwork, its physical address changes, but its protocol address remains same. IEEE has developed the hierarchical terminology that is useful in describing this process. The network devices without capability to forward packets between subnetworks are called end system, whereas network devices with these capabilities are called intermediate systems. Is are further divided into those that can communicate within routing domain and those that communicate both within and between routing domains. A routing domain is generally considered as portion of an internetwork under common administrative authority and is regulated by a particular set of administrative guidelines. Routing domains are also called as autonomous systems. Layer 4 switching. Layer 4 switching is considered a hardware-based Layer 3 switching technology that can also consider the application used. Layer 4 switching provides additional routing above Layer 3 by using the port numbers found in the transport layer header to make routing decisions. These port numbers are found in Request for Comment 1700 and reference the upper layer protocol, program, or application. Layer 4 information has been used to help make routing decisions for quite a while. For example, extended access lists can filter packets based on Layer 4 port numbers. Another example is accounting information gathered by open standards using S-Flow provided by companies like Arista Networks or proprietary solutions like NetFlow switching and Cisco's higher-end routers. The largest benefit of Layer 4 switching is that the network administrator can configure a Layer 4 switch to prioritize data traffic by application, which means a QoS can be defined for each user. For example, a number of users can be defined as a video group and be assigned more priority, or bandwidth, based on the need for video conferencing. Multi-layer switching. Multi-layer switching combines Layer 2, 3, and 4 switching technologies and provides high-speed scalability with low latency. It accomplishes this high combination of high-speed scalability with low latency by using huge filter tables based on the criteria designed by the network administrator. Multi-layer switching can move traffic at wire speed and also provide Layer 3 routing, which can remove the bottleneck from the network routers. This technology is based on the idea of route once, switch many. Multi-layer switching can make routing switching decisions based on the following: MAC source destination address in a data link frame, IP source destination address in the network layer header, protocol field in the network layer header, port source destination numbers in the transport layer header. There is no performance difference between a Layer 3 and a Layer 4 switch because the routing switching is all hardware-based. See also, network switch, content switch, residential gateway, references.